to what's called electrical ground. The symbol looks like this. Now, when we say electrical ground, we actually literally mean the ground, like the earth. You bury a big pipe in the dirt is often how it's done. Okay? What is the point of that? Well, the earth is a very large object. So it's basically a neutral object that can serve as a source or sink for electrons. So if you have excess electrons and you can dump them into the ground, but the ground is big enough to basically still remain neutral even though you just gave some charge to it. Because of course it has such a large amount of room to disperse. And likewise, if you need electrons, the Earth will be happy to give them up to you and still remain neutral because it's so big. So basically what we're going to use the Earth for here is a dumping ground for the excess charge. So here, these positive charges repelled all the way to the right side, they're just going to keep repelling even further away. So they're going to repel right into the ground, which means we no longer have half the charge polarization. So step 2, we connect B to ground, and we have that the half the charge polarization is canceled. So we have now an overall charge on B. B now has a net charge. It's positive. Now, you might say, well, why doesn't this positive charge doesn't like itself, it doesn't like hanging out with itself either. Why wouldn't that take the opportunity to escape? Well, it's pretty much super psyched about this negative charge, and so it's not going to take the opportunity to escape. Okay? And that, by the way, is the essence of how charging by induction works, is that A and B will always end up with opposite charge. If A you bring nearby is negative, then the charge that will end up being B on B will be positive. Or, positive. That's where you get the charge in the charging by induction. You get it because it's the half of the charge polarization that's attracted to your nearby object. Okay. Now we just have to clean up after ourselves and make sure we don't botch it in putting it away. So the last 2 steps have to go in this order. First, you have to disconnect ground. So that basically gets rid of the escape hatch. And then, once you've disconnected the escape hatch, you can take away the bait. Okay? So now you can remove A. Remember, A was the bait. Then that positive charge that we have on B, it will not stay on the left half. Remember, this is a conductor, so charge is mobile. So it will spread out, and B will look something like this. That excess charge will spread out on the surface, but of course it has nowhere further to go. If the ground connection was still there, then they would just then that would get neutralized with the ground as well. So that's why I want to make sure you disconnect the ground first, because if you don't keep A around, this charge won't stick around either. It will be gone. So make sure you understand why you have to disconnect the escape hatch first before you take away the bait. Then whatever charge you've generated on B will just redistribute along the surface. So that's the process of charging by induction. Now, as far as why it has to be a conductor specifically, notice that we are connecting the entire object by a single point to the ground, and assuming that everybody has means of transportation to get from that point to any other point that they need to. So for instance, these electrons are able to get to the escape hatch. So charge mobility is crucial in this process. Okay? So charging by induction, you have to have a conductor for the object that you're charging. It's not going to cut it with an insulator. So it's one of the few phenomenon where you cannot just say that an insulator does it half-assed. It doesn't do it at all because it doesn't have that charge mobility. I believe you guys get to try this process of charging by induction with a device in lab called an electrophorus. The electrophorus basically looks like a pie plate with a stick in it. All right? So the stick is just for you to be able to hold it, but basically it's that object, that pie plate is B. Okay? So let me explain how it works. What you do is you have some kind of flat base, and you rub it with some fur of unknown origin, okay? And then that becomes this. So this is the base of the electrophorus. And then you bring that plate, which is this thing, really close by. In fact, for all intents and purposes, it's going to look like you touched it. You have to believe me that there is enough of a gap there, okay? Because it's going to look, they're going to ask you to just set it down on the base. Then, playing the role of ground is you, your finger, you touch it. So when you touch the thing, you will take half the charge polarization off, and you are a big enough body that you can be a source or sink of electrons as needed. So this is you, this is your finger, is the ground connection, and you are essentially, your body is acting electrical ground. So then when you touch it with your finger, disconnect your finger, and then you will have charge on that. And I think what I don't remember what they have you do with it, maybe store it somewhere. Maybe have you discharge a little LED with it. And you can do it indefinitely, because the charge is essentially coming from the vast amount of charge carriers that are here that will polarize, and then you cancel half of them with your finger. Okay? So the configuration looks nothing like this cosmetically, but that's basically all you're doing. So remember, the base is A, the plate is B, and finger and U is ground. Are there any questions on that? Okay, so that right there, that discussion, you will find some questions on that stuff at the beginning part of your homework number 2. And I think there's 2 very many part multiple choice questions. You won't find that heavily featured on the homework simply because there's a limit to multiple choice questions on WebAssign, but this is excellent fodder for the multiple choice questions on your exam. Okay? So you will find when I post the practice materials, you'll find some practice multiple choice questions in that vein. The majority of your homework number 2 is on this thing called voltage. That's what we're doing next. Are there any questions before I change gears? Okay, so we're finally out of tangents. We are getting to the energy method. So that's what voltage has to do with. The energy method of handling this stuff. Okay. So here I want to introduce it in a way that makes the most sense to me. Let's make sure I do this in a way that makes sense. So I want to talk the force picture, and I want to talk the energy picture. So these are, of course, the 2 major models of discussing systems in Physics 1. And we can talk in the direct perspective or in the intermediary perspective, in both. So let's talk about that. Well, we started off the course, of course, saying that charges can directly interact with this thing called Coulomb's law. I guess let me put capital Q and lowercase q here to denote the 2 charges. And then we basically cleave that equation in half, and we let the intermediary between these two things be called the electric field. So we can talk about the cause side, that big Q causes an electric field, and we can talk about the effect side, where the other charge feels that field. So that was a useful construct to be able to break apart and discuss cause and effect on their own footings. Of course, many of those things are vectors. I'm just writing the magnitudes out right here, but remember that everything here are vectors. And that was one of the things that, of course, made it annoying to work with. Homework number 1, you have all your SOHCAHTOA and all that stuff, right? You have to do vector addition of forces, you have to do vector addition of fields, all that stuff, right? Well, the whole point of the energy picture was it allowed you to move to talking about numbers, scalars. It is probably your favorite technique from Physics 1, right? You just have your kinetic energy and potential energy and just check out what it is at first and then find that, no, it's the same later or whatever, right? So let me give you the equation for the potential energy that two charges have when they're near each other. And hopefully it's not a surprise that they have potential energy, right? If I have two charges and I release them, they both start moving, right? They either start moving because they're attracted or they move because they're repelled. More kinetic energy, right? Well, that kinetic energy can't come from nowhere. It comes from the stored potential energy that they have when they're put near each other. Now, I can't derive this for you, so you'll just have to take my word for it. It's one integral, but maybe some of you have no idea what that is. So that's just the formula, okay? So that gives right there the amount of energy, potential energy, I guess let's say electrical potential energy as well, that two charges have by being near each other. So first things first, differences from the force law, there's an r in the denominator, not an r squared, so be really careful about that. Also, there's no absolute value signs anymore. Here I specifically wanted absolute value signs because I wanted the force magnitude. Force is a vector, I just wanted its magnitude, and then I'm going to deal with the direction stuff separately. Here, these are all just numbers. So I'm just going to work with the numbers, and I'm going to work with both positive and negative numbers as well, okay? And that's okay. We're going to get used to the idea of what it means to have negative potential energy, which sometimes happens. But hopefully, since you're already adept at working with the electric field, hopefully we can cleave this apart right away so that we don't have to spend a separate discussion doing this directly. We can just jump to the middleman. So let's do that. So on the cause side and the effect side, so now what big Q makes is not the electric field out and everywhere into space. It makes what we call a voltage. That is the nickname for it. It's also known more formally as something called electric potential. I prefer voltage because electric potential is really easy to confuse with electric potential energy, which is not the same thing. So that's awkward. But as I will show you, first of all, it's universal language. You can't get away from it, so you're going to have to get used to it. And then I will more commonly refer to it as voltage, which is a lot easier to keep straight from potential energy. Let me put the effect side over here. So the other charge, little q, gets potential energy by sitting in the voltage made by the other charge. So you see that it looks pretty much like the same deal, right? It's the Same idea. We just now have a new middleman for energy called voltage. Before we had a middleman for force, which was called electric field. Now we have a middleman for energy, and that's called voltage. So just like before, we had this thing called the electric field. It's a local condition. It tells you about the space. So property of the location or property of the space. And then all you had to do was multiply that property at that location by the charge that you decide to put there, and this equation will tell you the force on it, right? So this ended up being the force on the charge. So that's a property of the object itself. Well, the new formula pretty much works the same way. There's this new intermediary called the voltage. It's a property of space. Where does it come from? Ultimately from other charges, but if you know the voltage at some location in space, all you have to do is multiply what charge you intend to put there, and it'll tell you something about that charge. So now it will tell you the potential energy that is stored by that charge. So notice that on the effect side, same deal. You have a property of space that's multiplied by what you decide to put there, and the outcome will be something that tells you about how that charge behaves, whether it tells you the force on that charge or the energy stored by that charge. Okay? So what I'd like to do is first explore this equation and just get used to all the signs and all that stuff, and then we'll come back to the cause. Let's see how much time we have left. Got another couple minutes here. So let's see what we can do today. So this equation, PE equals QV. Let's first take a look at the units. Does anyone remember the units of energy? Joules. What's the units of charge? SI? Coulombs. So we are forced to realize that this unit here for voltage is joules per coulomb. So what the voltage tells us is how many joules of energy are available at this location in space per coulomb that you put there. You just have to specify how many coulombs you actually want to put there, and then the equation will tell you how many joules of energy is stored. So the units of voltage are joules per coulomb. How much energy is available per charge, per unit charge? This gets a name, it's called a volt. So when you say 1 volt, what that means is that 1 joule of energy is available here for every coulomb of charge that you put there. So the unit itself is called the volt, and hence the nickname for this quantity is voltage. Okay, voltage is just a nickname based off the unit. It's like if we called mass kilogrammage. Okay, so the formal name is electric potential, but I'll call it voltage, and many people do. Okay, so let's go ahead and see if we can get a little bit of experimentation done. So I want to suppose that I have a spatial location over here where the voltage is plus 9 volts, and I have another over here where the voltage is plus 3 volts. So someone has been nice enough to tell me about the space. Now, I haven't drawn the voltage everywhere, but let me assume that somewhere between them is not like 1,000,000 volts, okay? So that would be like, if I gave you a roller coaster where there's a level here and a level here, I'm assuming there's no huge hill in between, okay? So I'm not specifying if it goes like this, or like this, or like this, but the voltage values in between are just some intermediate value, okay? So what I'm going to suppose is I have a charge of +1 coulomb. That's a lot of charge, but it's easier to do the computations. And I want to drop it in both spots and calculate how much energy it has. I guess let me also say that its mass is 1 kilogram. So if I calculate how much energy it has in both places, I guess I can label them over here. If I label this is going to be +9 joules, and this is going to be +3 joules. Okay? So remember, I'm just taking the voltage, which is joules per coulomb, multiplying it by 1, because the coulombs are 1. So we know from physics 1 that things like to go to lower potential energy, right? I drop a ball, it goes to lower potential energy. So if I were to pick a natural progression for this, it would be like this, right? So if I were to drop it on the left, it would move spontaneously to the right, but not vice versa. So things like to get to lower potential energy. So systems want to get to lower potential energy. And if there is no friction or any other non-conservative forces, oftentimes when you lower your potential energy, where does it end up? Semantic mechanical has potential as well. Kinetic energy, right? So we have our master energy equation. E is mechanical energy, which is kinetic plus potential. And if in the absence of non-conservative forces like friction, we just trade them, just like on a roller coaster. Okay? So if we dropped it over here at rest, which means no kinetic energy, we've established that the system overall has 9 joules of mechanical energy, right? We got to still have it over here, right? Energy is conserved. So how much kinetic energy is there at this point? 6 joules. So this thing is moving now with a final speed, and if it's 1 kilogram, you can calculate that speed. That speed, I believe, is 6.3 meters per second. It has a mass of 1 kilogram. I guess I should remind you, kinetic energy formula is 1/2 mv squared, right? Where v is the speed. Let me just double check that figure for you. No, I have something different. Don't quote me on this, but this may not be right. What, 1/2 mv squared is 6. What? This is 1. So square root of 12. Is that right? No, that's not right. What's square root of 12? Let's leave it as square root of 12. Okay. So that's whatever that is. That's your final speed. So you get the flavor of this. Just energy conservation. We'll do more on this next time. I just hit a bad spot, so I'll do more on Thursday.